Hi guys. Okay, so we're going to move on to the concept of lenses and mirrors. This is going to be put into 4 different videos. Now we're going to have to introduce ourselves to what our conceptual notion of lenses and mirrors looks like. And so let's go ahead and introduce ourselves to those and some key concepts so that we can start doing some calculations. All right, so the first thing is let's label the types of lenses that we have. And we have convex and concave. The convex lens is given, it looks sort of like this, okay? Convex and concave do opposite things. The concave lens looks kind of like this, okay? You can also have convex and concave mirror. Okay, so types of mirrors. Would be, so for the convex, you would have a mirror that looks like this, like it's like the side of a ball, for instance. Like if you've seen a Christmas ornament or something like that, you're not interested in that right side. It's only this shiny outside that you're interested in. So we might you could break off a piece of a metal sphere, and this would be a convex mirror. And then we have a concave mirror, which is the opposite, so it's like the inside of a spherical reflective surface, right? Okay, now obviously we also have flat mirrors, right? And then there's all the different kinds of shapes of mirrors, but in this particular section, we're focused on spherical mirrors. So really, if you want, you can put spherical mirrors. Also, the main types of lenses that we're dealing with in our course is called thin lenses. So you can get some pretty complex shapes going on with lenses, but we're going to focus primarily on the thin lens because it's mathematically more approachable. Okay, so for every lens, we're going to have something called an optical axis. And we're really going to be doing this with both the lens and the mirror. Okay, so the optical axis is I'm going to draw it over here on the right side. The optical axis, or I can make it a solid line, that's fine, is going to basically be the line of symmetry up and down for our particular mirror or lens. So let's go ahead and draw a lens. I'm going to choose to draw the convex lens, which we also call a positive lens, for reasons that will soon become clear. And I will not be drawing right now a concave lens, which we call a negative lens. Let's look at the basic setup for this. Okay, it's going to look something like this, where you can see that the lens is symmetrically divided by the optical axis. We're also going to have something called the optical plane that goes in the other direction. So the optical plane is basically the plane where all of the light that's on the left side of the lens or the right side of the lens is bent. Essentially, we model it as everything is bent along that plane. Now, in actuality, what's occurring here is if I have a ray of light, and I'm going to go ahead and use one that is parallel to the optical axis so that you can kind of see the action that happens with a lens. It's going to look something like this. So what occurs here is when it hits the first interface of the glass, it bends a little, and when it hits the second one, it bends some more. And then if we took another ray that is also parallel to the axis but not in the same position, it will have a similar behavior. And something that you'll notice is that they're both going to go through the same point. And so we actually have a name for that. It is called the focal point. And we use a little f to represent the focal point. The focal point is defined as exactly this, where when you have parallel rays of light on one side of a lens, then they will focus on the other side of the lens at exactly the focal point. Now, The focal point doesn't just exist on one side of the lens, it exists on both sides of the lens. And it exists equidistant on each side. So if this lens comes out of the factory with a 10 centimeter focal length, then you can guess that parallel rays of light will focus 10 centimeters on the other side, and if you flip it around, you'll get the same thing on this side. So the focal length is 10 centimeters on both sides for the particular lens that you bought at that store. Now, these of course could have different focal lengths, right? Well, what does this do? What it does is it rearranges where the image forms of an object. Now, we looked at image formation in terms of mirrors before, but now we are going to talk about image formation in terms of lenses. What is an image? Well, an image is where something appears to be, and so you do have some familiarity with that from the mirrors, but it's going to be a little bit more complicated than that with the lenses because we have, in fact, for the mirrors and the lenses that are curved, we have two different kinds of images. It turned out for the flat mirrors, the images were always virtual images. They were never real. And the reason is because you never saw light coming from that spot. You just thought you did. So for a flat mirror, all images appear virtual because the light appears to be coming from that point, but is not coming from that point. So any image that is virtual is going to have that characteristic. If light seems like it's coming from there, but it's not actually coming from there, that's a virtual image. If light seems to be coming from a place that is not an object, but the light actually is coming from that place, then that is not a virtual image, it's a real image, and those can be formed using lenses. So, as well as some mirrors. So, let's look at what that means. The number one thing that starts off confusing about lenses and mirrors is what object and image look like in our diagrams. Let's clear that up real quick. If I have over here on this side of the lens, I have a book. I really do not want to have to go through the process of drawing out the book and considering all three dimensions of the book every time I want to think about an image. And I know that this effect, the image formation effect, is going to occur symmetrically about the optical axis. So there's really no reason for me to go into all the trouble of creating something that looks like this when I can just have something that has about that same height. I can have a very simple looking representation or an icon that represents my particular object, because it's not really the fact that this is a book that I'm interested in, it's the lens that I'm interested in. I want to know how the lens behaves. So, rather than writing this book, I'm just going to write an arrow to represent the height of the book. So I'm going to use just a very simple arrow there. That's not actually as simple as we usually will use, but a simple arrow there to represent the placement and height of an object. In other words, I'm interested in how far away the object is from the lens, and I'm interested in how tall the object is, so the size of the object, right? Okay, so there are two things that I'm going to use to represent that, and the first one is the height, which I'll give as h, and then also want the distance away from the mirror. So I'm going to take the middle of this thing and represent its distance away from the optical plane, the middle of this lens here, okay? That distance is going to be called P, okay? The object distance. I now am interested, now that I know the height of my object, I know the height of my, the location of my object with respect to the middle of the lens. I'm also interested in where the image is going to form due to this object, and I don't know necessarily where that is until I calculate it out. So your first intuition might be that this image is going to form over here on the other side of the lens. I think you might be surprised to find, though, again, yeah, it's a guess on my part, but I'm guessing this is going to end up very large and somewhere behind the lens, very big and somewhere behind the lens and pointed upward. So let's go through some equations so that we can get a sense of how close I was. There's going to be two main equations, and the exciting thing about this is that those equations are going to be useful for both lenses and for mirrors. Okay? So here is your main equation. It is the lens equation. 1 over the focal length, that is the distance from the middle of the lens to that point F, is equal to 1 over the distance to the object, P, plus 1 over the distance to the image, which we're going to label as Q. So we don't know where Q is, so I'm not labeling it on here yet, okay? But that's going to be our first and very important equation. Our second equation is really, it's technically two equations, but I like that one of them is just a definition, so I like to write it as one equation, okay? It is the magnification equation. It's given as the magnification of the image is defined as the height of the image, which I'll give as h prime, divided by the height of the object. Okay, and if it's negative, then that means it's upside down, and if it's positive, that means it's right side up. So this is also going to be equal to, and this is where the real magic of the equation comes in, is also going to be equal to the negative of the image distance that we saw in the previous equation over the object distance that we saw in the previous equation. So basically, if you know these two equation sets, then you're fine for the rest of this, okay? Now, the thing that you're really going to have to pay attention to is where the negatives are in this. The rest of it is not that different than just doing like a parallel resistors equation or something like that. So, that being said, let's go ahead and do some measurements here and calculate out where we would expect this to be, okay? Now, looking at the lengths that we have here, let's use our ruler real quick. And the ruler is, so I don't want to do too much with this, or too much. Let's say that we have a 10 centimeter focal length, okay? If that's 10 centimeters, and we were to take that same 10 centimeters and put it over here, then we can see that the object distance here is a little bit more than, let's see, that's 10, and that would be 20. So this would be about 15. So we could probably say that the object distance is about 16 centimeters, okay? So let's go ahead and presume that that's located at 16 centimeters. In fact, the object distance should be labeled from the top of the object to the optical plane, the point of the object to the optical plane. So I measured it to the middle of this arrow. So we have labeled then that our object distance, P, is equal to 16 centimeters. Now, something very crucial here. It's positive. It's always positive. You can even think of the letter P as being that it stands for positive. The object length, or the object distance, P, is always positive. It defines what positive and negative is for the particular problem that you're facing. The image distance, we do not know, right? We can go ahead and calculate a height, or we could at least estimate a height here. So if we had this as a 10 centimeter length here, that's not quite 10 centimeters, it's more like 8. Also, it's about maybe a little less than that actually. So it's a little less than half the length to the lens. So let's say 7 centimeters. We'll give it a height of 7 centimeters. Okay. And again, this isn't going to be an estimate. Later, we would prefer to be able to do this precisely, and we will do it more precisely in the future. Okay. So when we do ray tracing, we'll have to be very precise. But this is just a visual estimate. The calculations are going to be precise. Okay. So if we have the height of this thing is 7 centimeters, we can actually know exactly what the image is going to look like now. All we have to do, if we know that the focal length is equal to 10 centimeters, and is this positive or negative? Well, the thing is, I mentioned before that this was labeled as a positive lens. This is why. Because this particular type of lens, the convex lens, is a positive lens. That means its focal length is also positive. Okay. Now, again, we'll go back over more of that later to make sure you're clear about which focal lengths are positive and which ones are negative. So, but right now, let's just address the equation. So, we need to solve for Q. We need to know where the thing is located, and we need to know how big it is in the image and what direction it's facing. So, let's do this. Solve the upper equation for Q. In order to do that, we would then subtract both sides, 1 over P from both sides. So we would get that 1 over Q here is going to be equal to 1 over F minus 1 over P. And then, of course, if we wanted to solve for Q, we would need to do just like we do with our, if we wanted to solve for Q, not 1 over Q, we'd have to do just like we do with our resistor equations, where we have 1 over F minus 1 over P, and then flip that answer to find Q, okay? Let's plug that in, and remember, your negative signs are important here, so you'll always want to know whether your Q is negative or your focal length is negative. Those always make a difference, okay? So we get 1 over 10 minus 1 over 16, and that's going to be inverse centimeters, right? To the negative 1, and that'll be in terms of centimeters, right? Now, again, just like with your resistors, you can plug this in as 10 flipped minus 16 flipped and then flip, right? So inverse 10 minus inverse 16 and then inverse. So let's see, that's going to be, you can do this in fractions or you can do it by the calculator. I tend to like the fractions. This is going to be, I could do 16 over 160 minus 10 over 160 flipped. This is interesting. It looks like my guess was off. I can tell now that I was wrong. It is not going to show up behind this thing. It's actually going to be where you would have originally expected it to be, which is over on the other side of the lens. Yeah, I guess I make mistakes. It's cool. I make mistakes. You can make mistakes too, right? Okay, so but the calculations will not make, as long as you get your calculations correct, we will find it, right? This doesn't hurt to guess as long as we back it up with mathematics. This is going to be 16 minus 10 is 6 over 160, right? Which is 3 over 80. So it's going to give us then, if we flip it, 80 over 3. Now, if you did a calculation on that, you probably will have gotten, it's like 26 and 2/3 centimeters, and that's positive. If you and I had put a bet down and you just said the image was on the right and I said it was on the left, you would have won the bet. Okay, so I should have been more careful so I can make my money. All right, so let's see here. What's next? What does this mean? 26 and 2/3 centimeters. The image shows up 26 cent. Looks like we have to move this thing over a little bit because it's not. Let's make sure that this is where we can move this thing over a little bit. We got to make sure we can that we have enough room for where the image is going to show up. Okay, the 26. Good gosh, that's let's see. That's going to be, here's 10. That's about 20. And then another 6. So it's still really pushing it over here. All right, so we know that this thing is going to be located right here. Okay, that X marks the spot here. Okay. Now, if, or that say it's even a little larger than that, but we'll take it as, we'll put it at the edge of the screen because I ran out of screen. So now, the rest of this, what is it? Is it up or down? What's the size of it? That can all be solved by the magnification equation. Okay? Now, how did I know that it goes this side and not this side? Well, the image is always positive. I'm going to write this out in red real quick. I'm going to have to erase it because I need some space. But so the rule on this is the image is positive when it's formed where light is expected to go. I know that seems a little cryptic, but it's going to be quite useful of a rule for Q. For a lens, what does a lens do to light? Well, it lets light through it, right? So if light goes through the lens, then if it forms on the other side of the lens, then your image is positive. And if it's on the same side as the object, then it's negative. Now, that's going to change for mirrors, and if you want to go through and memorize all that stuff, then that's fine. If you don't like this way, you can memorize which things are negative and positive, where your book has tables that represent all that. I like simple rules to help me remember, so I don't have to think about it, or try to remember. I don't mind thinking about it, but I don't like to remember. So the image is positive when it's formed where light should go. Light should go through lenses, therefore it's positive if it's over here. It's negative if it's over here, right? What about its magnification? Well, its magnification is going to be equal to, according to our equation up here, is going to be equal to negative, what is Q? Now this is where you have to also be careful about negative signs, because if we have a negative Q, we need to put a negative of a negative. But we do not have a negative Q, we have a positive Q, so it's going to be negative 26, or you know what, let's say a negative 80 over 3, I like that a little better, over, and what's P? P is over 16, right? It didn't turn out as well as I hoped. We're probably better off saying it's negative 26.7 over 16, okay? It's a little easier to put in our calculator. Negative 6, oh, that's not right. Negative 1 point, we'll say negative 1.7, okay? Negative 1.7. All right, so that means that it is basically 70% larger. It means that it is 1.7 times the size of our object. And since we said our object was about 7 centimeters, then we can apply that to this portion of the equation here to say that the image height is actually going to be equal to the magnification times the height of the object. So 7 centimeters times 1.7, which should give us 1.1, or excuse me, 11.7, right? So it's 11 point, or it's about 12, okay, about 12 centimeters. So that gives us something that looks, let's see, this is 10 centimeters here, 12 would be here, so it's actually going to be this big here. Oh, oops. Sorry. That's a negative magnification, so it should be negative. Okay, so it's going to look something like this. Our image shows up somewhere around there, okay? Okay, this is an important process. This, the height portion of the equation tells you how tall it's going to be. The negative here tells you whether it's upside down or not. And solving for Q tells you where it's located along the optical axis. Okay. This is a general idea. I want to do one more before we end the video so that we can be absolutely clear about how to solve some of these equations. Okay. Let's go through now the process of a concave lens or a negative lens. And I don't really actually have to draw it out for you, but we can say, okay, here's your lens, all right, and we have an object that is let's say it's 30 centimeters in front of our lens, okay? So that means that the object distance is 30 centimeters. It's always positive because it's the object distance. The focal length is going to be 10 centimeters again, let's say. Okay, so let's say there's 1, 2, 3. Okay. Still on both sides of the lens, just like before, only the difference here is that because this is a negative lens, I'm going to write that as negative 10 centimeters, not positive. Now, if we want to find out where Q is, it's not that hard for us. We have to actually go through the same process. Now, sometimes you're going to be asked to solve for P. Sometimes you're going to be asked to solve for the focal length. So far, all we've done is solve for Q, but it's the same equation, just different algebra, right? So again, we can go through the process of subtracting out 1 over P and then taking the flips. So 1 minus F minus 1 over P, so 1 over F minus 1 over P to the negative 1 is going to be equal to, okay, what's our focal length? Remember, this is a negative this time, right? Minus positive, right? This fraction is a little easier to deal with here. We get a negative 3/30 minus 1/30 flipped is going to be negative 4 over 30. So that means we get 30 over 4, which gives us a negative 7.5 centimeters. And at negative 7.5 centimeter image distance, we have to ask again, hey, what does a negative sign mean here? Well, remember, for Q, when the image forms where light is supposed to go, then we get a positive image distance. But if the image is forming where we would not expect light to go, we get a negative image distance. This is a lens. Light goes through lenses. So if it's over here, it's positive, and if it's not, it's negative. So this is a negative image, so we'd expect it to show up over here. Now, the image distance is given as 7.5, so since this is a 10 centimeter length right here, then we would expect it to be 3/4 of the way there. We do not know, I'm going to mark an X there, we do not know whether that is located, whether that's going to be up or down or how big it is, right? So let's find that out. We can again solve for the magnification as negative Q over P. We have a negative of our image distance, which is negative 7.5 centimeters here. And then a positive object distance, 30 centimeters, right? 7.5 is just 1/4 of 30, right? So that means that this reduces to a positive 1 over 4. This means, since this is less than 1, you could write it as 0.25 if you want. This magnification is 1/4 the size of the object. The image is going to be 1/4 the size of the object. So, or by this portion of the equation, we could solve that as the image height is going to be equal to 1/4 the object height, right? And we notice that it's positive, so it's up. So it's going to be actually a tiny little arrow right there. Let me erase this stuff. Put a little tiny one in here. Here's our image right there. Little tiny arrow. All right. Hopefully this kind of gives you a general idea about the calculations on these things. I'm going to go ahead and do another video where we just describe the characteristics of the mirror. And the good news is this equation works for both the lens and the mirror. So we're just basically going to go through the two types of mirrors and get more practice using this equation.